Boa tarde, todos e todas. Eu só gostaria que me confirmassem se vocês estão ouvindo bem. O pessoal que está de fora da...
Aqui está ok.
Sim.
Ok. Tudo bem. Bom, nós vamos iniciar, então, nosso seminário dessa tarde. Vai ser apresentado pelo nosso estagiário de pós-doc, Hosein, e hoje ele vai, né, um pouco na sequência da apresentação da semana passada, seguir tratando de aplicações de fuzzy adaptativo, e ele vai focalizar, como comentado na semana passada, que eles puderam acompanhar, né, aplicações em sistemas caóticos e aplicações, né, na parte de eletrônica de potência e vinculadas aí a microredes. Então, queria agradecer a presença de todo mundo que está acompanhando aqui localmente, também remotamente, né? Eu vou manter aqui o chat aberto, então, se alguém tiver alguma questão, alguma dúvida, pode colocar por aqui, que eu, né, repasso a informação para o Hosein, né, para que ele possa comentar e responder. Certo? So, Hosein, thank you for your presentation. I will be reading the chat, so somebody put it in web.
Sure, thank you.
Okay?
Okay, thank you very much. So, hello, dear audience, all dear professors, dear researchers, students, and warmly welcome to this presentation. I hope it can be useful for you and effective, and you use in your future works. And I hope it can give you the new overview about power electronics and microgrids. First of all, thanks for Professor Antenor and Professor Juan for arranging this seminar for us. And I'm going to start. The subject is adaptive fuzzy control for chaotic systems and their application in power electronics and microgrids. As you can remember, in the previous seminar, we introduced fuzzy type 2, and we introduced that the capability of fuzzy type 2 is much more effective than fuzzy type 1. And researchers that works with intelligent control nowadays get focused on fuzzy type 2. Of course, fuzzy type 2, when Professor Lotfizadeh was in life, he introduced fuzzy type 2, but other researchers continue his works. And nowadays, we also develop fuzzy type 2 to fuzzy type 3. But since fuzzy type 2 still is a hot topic for nonlinear systems, I'm going to present this seminar by fuzzy type 2. Of course, in the future seminar, we will switch to fuzzy type 3. For the just brief introduction, as you can see, the membership function of fuzzy type 2 also is fuzzy. In the fuzzy type 1, just we have the one direction. In fuzzy type 2, we have two directions. So it can increase the capability of fuzzy type 2. This is the general structure. First, we need, at first, we are working with some numbers. Then we need to make them fuzzy by membership function. Then we have some rules and the fuzzier, and after the fuzzier, type reductor, and again numbers. So all this process is the general, perspective of fuzzy system. But since our subject today is chaos and chaotic behavior of power electronics and microgrids, so at first I'm going to introduce chaos. What is chaos? As you can see, if I want to introduce chaos in a simple word, chaos is kind of behavior of systems that the response of every system is randomly. We cannot predict the response of the system. So this kind of behavior for systems is very difficult to control because the behavior is random. There is no prediction for behavior. For example, system type 1 or their 2 or their 3, they have a you can predict their behavior, at least in which boundary they behave. But in chaotic system, no, there is no prediction. So that's why it makes the system more complex. I will show you in the following PPT how it works. But now just we are going to introduce it. For example, as a practical example, flapping of the wings of butterfly in one country can lead to storm in another country. For example, in Brazil, we have a butterfly start to, flapping, so it can make a storm. For example, in Colombia, we call this action as a chaos, because you cannot predict the behavior of weather. The dynamic of the weather is highly nonlinear and chaotic. So this is the overview of chaos based on mathematics. But let's see. I'm going in the following PPT. For example, this is this. How much is sensitive? For example, the system started from 5 and then start to act chaotically. You cannot find what is the behavior of system, even frequency change, domain change, time, everything changing. So we call it chaos system. Many industrial systems can act chaotically, like robotic, like power electronics, like microgrids, like economic. That's in the. These are 3 important chaotic systems. The first one is novel. Lorenz and Chen. The name was the name of scientists that discovered this kind of behavior. For example, we can simulate some behavior of system by the equation that the scientists discovered. For example, maybe microgrid act chaotically as same as or similar to Chen chaos system. Chen discovered a standard equation for chaos system. We call it Chen chaos system. So maybe your microgrid acts similar to Chen chaotic system. So these are, of course, we have much more, type of chaotic systems nowadays because researchers work on them. But these 3 are very famous and basic. The different system that maybe they can act chaotically. So our group is power electronic. Of course, it can be, applied for telecommunication, communication, satellites, and in this kind of area. For mechanical systems, also very good, subject for investigation about the chaotic systems. About economic, I think in the previous seminar I discussed with economic system. For example, if I want to give you the example, is COVID-19. COVID-19 in economic system make economic system act as chaos. You cannot even predict simple thing about behavior of economic system, and voice recognition and some digital electronics. These are much more important systems that act chaotically. So when you're going to design a controller, when you're going to use the mathematical dynamic, you need to sometimes you will face with chaotic behavior of the systems. So the challenge, why chaos or chaotic systems are very important, because they have a complicated dynamics. In the term of mathematics, they make the dynamic much more complicated than the simple nonlinear one. Unpredictable, as I told you, you cannot predict the performance and behavior of the system. And they are very sensitive to initial conditions. Initial conditions mean when you start the system. Okay? When you, for example, put your hand on a start, when system start working, because it's very sensitive. And the behavior is different, for example, which the performance of system start changing, but if you change the initial condition of the system. So it's, these 3 challenge make chaotic system to be valuable and good, subject for investigation. The first work that I designed in Shanghai City Center was about robust fuzzy control for fractional order systems. Fractional order is kind of a specific type of mathematics. If you search, you can find this kind of a you can describe your equation by fractional order systems. It has its own advantage that, can be, for example, some systems can be described by this type of fractional order. So I go past from the I mean, just I want to show you how chaotic system, this is the dynamic of the system. But what is the novelty in this work? We consider we don't have any information about function, about F, about D is disturbance, and about inputs. I mean, we don't know the dynamic and equation of all these functions. And also we consider this Qi, that is the coefficient of chaotic system, is unknown. And based on this consideration, we designed, by of course employing fuzzy system, we try to design a controller. So maybe it's just pure mathematics, but in the following slide, I will introduce how your, for example, power electronic or microgrid can have the similar dynamic. Just it's a mathematical dynamic. Many systems you can simulate. The dynamic is exactly same as this. So it's kind of fractional order chaotic systems. The novelty of this work is all these equations are unknown. We don't have any information about them. So we designed a fuzzy system, fuzzy type 2, based on this consideration. But we trained the fuzzy type 2 by UKF, filter Kalman, because filter Kalman is a good estimator. For the arranging the membership functions of the fuzzy, we hired the fuzzy, filter Kalman filter algorithm. And so I'm going to show you the results. Is training of filter Kalman, how filter Kalman, we implement filter Kalman to train the membership function and the results. So this is the overview, general overview system. As you can see, this is the system. This is the estimator. We here hire fuzzy type 2, and we give the dynamic to the controller that we discovered by fuzzy type 2. We give the dynamic to controller, and as you can see, the result is quite desirable. So I'm going past because it's proving the stability of the system, as is very important in control, because when you design your controller, you have to prove the system is stable. And we have a different type of stability, just not one. And we have a different type of tool for proving stability, Lyapunov, Barbalet lemma, and many kind of stability that can be applied. So here we, hire the Barbalet lemma and Lyapunov and prove the stability. So we design this controller and implement on different type of chaotic system. For example, here is the Lorenz system. As you can see, this is a system, chaotic system. Of course, here we have the value, but we consider systems unknown. We don't have any information about it. Tracking performance, as you can see, it's exactly follow the references without any fluctuation. Results are quite smooth based on the references, and there is no fluctuation and oscillation. So if you want design this type of, design a controller for this type of chaotic system, for example, by PID, you will face a lot of problem because PID cannot endure, or even some classical method. And what is the novelty again? We don't have any information about these functions. We consider fault, disturbance is unknown, input, some problem that we have in input is unknown, and also we don't know the equation of this. Also, this coefficient is unknown. So as you can see, fuzzy type 2 has this power to have a smooth signals. The control signal is very important part in control science and engineering. As you can see, the control signal is quite smooth without any fluctuation. So it can be implemented. As I told you in the previous seminar, when you design a controller, when you have a control, your control signal is one of the important part of your work. Because if the control signal, they are not smooth, you cannot implement the work. And you will face problems. Here is comparison. Also, we apply this control on another type of chaotic system, the hyper-chaotic chain system. And again, if you look at the performance is quite good and control signal is smooth. Another chaotic systems, novel system, again, and tracking, because just the important part is reference. The chaos Y1 and X1, it's totally follow its reference without any problem, as you can see. Here, just maybe we have a few fluctuation in control signals, but it's acceptable for this system. Because if you compare this control signal with other works, the other works control signal, even they don't show because the control signal has a lot of fluctuation. But in our work, so at least it's acceptable. This can be implemented. This is the mathematical, tools for showing the chaos behavior. I will tell you in the following for power electronic. Another work is the general type 2 fuzzy for multi-switching synchronization, fractional order chaotic systems. These synchronization can happen in power electronic a lot because you have this switching. And so applying the fuzzy type 2 for this type of system, I'm going to show you the result. We have two systems, system 1 and system 2. Of course, it's mathematics. Maybe when you look at the equation, so it's just this mathematics. But as I told you, many systems you can simulate by this. At least they behave the same as the systems. System 1 and system 2. One system is master and another system is a slave. Which need to, like multi-agent, need to follow. The slave need to follow master and do switching. Switching between the state of the system. So we designed fuzzy type 2. I go past from the designing to show you the result. This is the structure of fuzzy. I described estimated the system and give it to the controller and compensator. This is the switching between state of systems. As you can see, because we have two systems with many states and it's switching. But we consider this switching in different mood, randomly and in different time to see what is the behavior of the controller. Controller can endure or can't. This is the structure of fuzzy type 2. The membership function, as you can see, I discussed at the beginning of the seminar about fuzzy type 2. We have a different type of membership function you can consider, and you can design your fuzzy system. That's a novelty. Here is designing. So I go past from the design. Finding the control signal, proving stability, and by using the Barbalet lemma, we prove the system is asymptotically stable. Asymptotically stable is kind of the strong stability. If you prove in your work system is asymptotically stable, so your system is stable. So this is the equation. You need to find the Lyapunov function, then find the condition to prove the stability. So I go past because I just want to show you the result, how much fuzzy system is strong for chaotic systems. We implement in two important chaos systems, as you can see. Okay, one of them is master, another one is slave, port switching. So let's see the behavior of, system. You can see at first the switching mode is here. System master, slave, and master system and a slave system. A slave system try to follow master system and do switching. You can see the result. Switching happens without any problem. Directly follow. Okay. In another mode, we change also the time. For example, switching happens also between different state of system in different time. Again, switching follow without any problem. Okay. This maybe can happen in power electronics. We tell you. Another system, another chaos system, master and slave, Nobel and Chen, two famous chaos systems. Again, but in this kind of synchronization, still we have this novelty that we don't know coefficient and we don't know these equations. When you want to design a controller, if you have this parameter, so it's easy. Of course, it's not easy it's because you will face some problems. For example, a sliding mode, backstepping, feedback linearization, PID, every type of controller you choose, it's difficult to design a controller because you need to prove stability. But the novelty of fuzzy here, even we don't have any information about this in our work. So again, you can see the switching in different mode and different time without any problem. This is the kind of mathematics way to prove system doesn't have chaotic behavior. So I pass it fast because it's mathematics. Comparison. And the last work that I'm going to pass soon is designing by fuzzy type 3. We designed the higher fuzzy type 3 to design a controller for chaos systems. Just to show you the result. We consider this class of chaotic systems. Again, we consider systems unknown function, external disturbance also is unknown, and inputs of the, control inputs also is nonlinear. So, as a general overview, we hire the fuzzy type 3 to act as observer and give the result to controller, and this is our chaotic systems. Okay, so let's see the result. So designing fuzzy. This is the membership function fuzzy type 3. This fuzzy type 3 has 3 directions that we hired here. Why we use fuzzy type 3? Because it has more capability to estimate nonlinearity. This is the proving stability and result. Just to show. This is the result. Tracking error, following the reference, control signal without problem. State estimation error without any problem. Another chaos systems, we implement the controller, another chaos systems, and tracking performance without any problem. So I'm going fast because it's much mathematics. I don't want to make my seminar boring. But I want to reach to this point. How fuzzy and how chaos system act in power electronics. The first challenge that we find in power electronics, if the equation that describe your converter or your microgrid become chaotic, so you cannot use the linear method that we used, even practically. Sometimes you faced many problems, you're looking for another problems because your system act chaotically and you don't know. You're looking for harmonic. You're looking to removing something. You're trying to, adjust the gain of your controller because your system is chaotic behavior. When your system act chaotically, it's make it difficult to control and unstable. Proving stability in this case is really difficult. You need to find the Lyapunov function again. Go through the condition of Lyapunov function to make it stable, and it's impossible. It's become much more worse when the power electronic converters connected to microgrids. Because I will show you, for especially PV. PV make the dynamic of power electronic much more complicated and make it to act chaotic. Okay. So this is the challenge you can find in power electronics. The first challenge, you cannot use PI and PID easily. And even if you use maybe PID control, but you face a lot of problem, a lot of, for example, noise. You can prove you have a lot of harmonic in your system that you need to hire another tools to remove this harmonic. System act chaotically, but you don't know actually. You think it's another problem of the system. Another thing is difficult to control. You need to find a way. You try to design a controller. So you go through the mathematics. You design a controller, for example, by sliding mode, for example. But implementation is difficult. You want to see practically, it's difficult. You cannot practical implement it because it's expensive. You need a huge computer. Another issue, when you connect it to PV, it's become much more complex and much more problem comes out. I will show you. So the question that you ask me here is how you can find system acts chaotically, how we can find this behavior. 3 ways: by simulation, of course, in simulation that you simulate on MATLAB or any Python or any other software, you will face this. In experimental result that you get, you see that your signal has many different frequencies. And in theoretical mathematical modeling, when you extract the model of the system by some identification, you will see the system exactly has the similar dynamic of some famous chaotic systems. So these three ways that we work, we can recognize chaotic systems. But what kind of tools we have to see the system is chaos? Let's go through the power electronics performance. Most of the power electronic operates at the desired point of equilibrium. I mean, you set the power electronic to work on a specific point. When your system, in the normal condition, everything is normal. Of course, your system works. But when the problem comes out, when system face some external and internal disturbances, I will introduce what kind of course, you can also do research about the different type of disturbances that's involving to your system. This is the meaning of control. Control when the system is normal. So control just simple. When control happens, when control appears to your system, when you have disturbance, when some parameter of the system start varying, start changing during the time. For example, voltage in PV. I will show you by some equation. Voltage in PV start varying, you connect this PV to the power electronic, so make all the system variable. We introduce bifurcations. What is bifurcations? Let me give you the example. Have you smoked? When you smoke, when the smoke comes out from your mouth, the smoke go to 2 ways or 3 ways, right? But you cannot find exactly go to which way. We call it bifurcations. Again, it's kind of way, it's not complete way, but it's kind of way to show, to find system act chaotic. Depends on which point system start act like a bifurcation. I will show you how it acts in power electronic. Depends on the point of working. This is bifurcation. For example, is a capacitor and gain. You try to change the gain from here to here. System is not chaotic. System work normal. Here to here, we call it semi-chaotic. Start to become chaotic. From here, bifurcation happens. System has different type of operation. Which one is correct? We don't know. This is the properties of chaotic system. So bifurcation is one of the tools that you can find the chaotic behavior in the system. We call it bifurcation. It's mathematics. You can search about it, but it's kind of, in MATLAB also we have some coding to find the bifurcation. If you apply this code to your equation, you can find how it's the results. Many times your converter try to act like this. For example, this is another bifurcation. It's for buck converter. Inductance and voltage. From here to here, not chaotic, it's normal. But here, why? Because this inductance is variable. Start changing during working, and you didn't consider it. I gave you this example in the previous seminar. The resistance in induction motor rotor changed during the time, right? So it was kind of variable parameter. Here, the variable parameter is inductance. Start changing, and bifurcation happens from here. You can see even it's become to 4 points, 4 different response of tracking. We call it chaotic. System act chaotic. Your converter. I introduced some famous internal disturbance and external disturbances that come to your converters to make your converter chaotic. For example, capacitance. Sometimes a capacitance that is involving in your converter. The semiconductors that your converter created by them, built by them, they act nonlinear, and sometimes they act chaotically. Right? So we call the internal disturbances. Of course, we have more internal disturbances you can find. How? By research. Other researchers' works. By experimental results that you get. And external disturbances like terminal change, like conduction, like radiation. So these are the external disturbances. This disturbances in many works that I read the paper, even with experimental result or without experimental result, are ignored. People didn't consider these disturbances, and they design a controller. So it's normal condition. System work normally. We don't have any problem. When problem happens, when you consider disturbances in the system. Variable parameter. Which parameter of your system start varying? Then problem comes out. We have two ways to find the chaotic behavior of your converter, your work. When you simulate your work, you can use the phase part rate, or you can use the, normal way. Here we call time domain rainfall. Of course, here is much more clear to find the chaotic behavior of your system. Okay. From the previous or prior example I showed you about converter, buck converter. For example, here we don't have any chaotic behavior. Here we don't have any chaos. If it's just one cycle. Here is semi-chaos, start going to saturation of chaos, because it's start to go into several repetition, but it's left. If in phase part rate, you have this behavior, that the cycle start to repeating, definitely is chaos. By waveform, you can see here. Frequency change, domain change, but how frequency change, I don't know. Based on which rule frequency change, we don't know. Based on which rule domain change, also we don't know. You're in oscilloscope, many times you see this, and you don't know what's the problem, because the system is chaos. So these two tools. Of course, we have another tool to find the chaotic behavior. We call it fast Fourier transformer, FFT. FFT is coming from sampling. If you want to use MATLAB coding or Python coding, there is a specific code for this. You can write coding for this. It's shown for you. Here, without any chaotic, here semi-chaotic, and here totally chaotic. These three tools for finding the chaotic performance of the system for microgrids. Here is an example. I want to show you two equations of PV. In most cases, when these converters, any converters, both converters, connected to photovoltaic systems, due to changing parameters, they can make the system, they can make the converter to have a variation in input voltage. If you consider these two equations for the PV, this is the current based on voltage and power based on voltage. This V can be changing, can be varying based on the time, based on the solar, based on the temperature. And you connect this PV to converter. So it's kind of variable parameter. If you discover the whole loop, because when you design controller, you have a whole closed loop, sensors, systems, converter, microgrid, everything. And when you discover the whole loop and design the control, you can see maybe it can make your system to work as kits. And this is the showing, for example, the voltage based on current for PV, as you can see, is variable. It's not constant. In wind turbine too. In wind turbine also we have this issue that connected to. So I hope this seminar gave you the whole overview about chaotic behavior of system. Of course, many researchers nowadays start working with chaotic behavior of the system, especially in microgrids and converters. And to find this nonlinear behavior that we call it chaos, still there is a huge area to work, and still there is a many problem that didn't solve, based on frequency control, based on voltage control, based on power control. And there is a difference between the nonlinear behavior of system and chaotic behavior of system. Because in nonlinear, at least it's much easier to control. But when system acts chaotically, it's much more difficult. And as I showed you, you will face a lot of problems, especially in finding the Lyapunov function or other tools to prove stability. Because again, in control, the much more important part is proving stability when you have a closed loop system. Otherwise, the rest is just design. Thank you very much for your attention. If you have any question, I'm here to reply.
Thank you, Hosein, for the presentation. So, again, some questions. Hosein, in my experience in this kind of problem, very small experience, but relate to Fourier ones, the main cause to have this kind of chaotic behavior is due to the saturation of magnetic devices. Because it changes the inductance, and you have the hysteresis, and it's very complicated. So I again, more or less easy to understand how it's possible to change things along a cycle at a shot. But okay, it's if we are able to design magnetic devices not to avoid, because a very work in the linear region, usually what we do. But if you follow the change, so we can enter in the non-linear part and we lose the design. Okay, so I can understand that magnetic devices can be a cause of this kind of problem. But it was not clear how the fuzzy can solve the problem, maintain the control of the system, even if what will happen? The fuzzy will avoid this kind of problem. We will put the system.
No, fuzzy, because fuzzy, the main important advantage of hiring fuzzy is not dependent on mathematic model of the system.
Mm-hmm.
So this is very important. In classical way, all the controller that you design depends on mathematic model. Sometimes extracting this mathematic model is difficult, because, for example, you have equipment here, but we don't have the exact modeling of the system. But for fuzzy, we don't need this. We have some other things to, enter to the system to extract for us. In the previous seminar, I discussed about it that we have a direct adaptive fuzzy and indirect. In indirect, so fuzzy first extract the model, then we give it to the controller. So here also can be the same, based on some another information, depends on your request. For example, what kind of problem you're going to solve. Then we can design the fuzzy, extract the whole model of the system, then give it to the controller for design. So this is the fuzzy. But sometimes fuzzy act as an observer. For example, you have some sensors that they're expensive or not available, so fuzzy can observe the state of the system. Depends on the problem that we are going to solve. And as I showed in the, chaotic system like Lorenz, like Chen, we design by fuzzy. We consider system is totally unknown. We don't have any information about the systems and we design. So this is the innovation of intelligent control nowadays over classical control method. But the problem is we need to consider the disturbances, as you mentioned, into the dynamic of the system.
But if you consider this waveform, where have the buck converter,
right?
Maybe have the inductance and the capacitor, and with just a moment, the microphone here. No, mine was. But if you consider this case of saturation of the magnetic device, this will happen in the tens of kilohertz. And I for the fuzzy system to identify how to implement this. I needed to sample the current voltage in megahertz to be able to identify the problem.
For implementation.
Yeah.
So we have two ways. The first way is just using the MATLAB at first to simulate this controller that we design can be, trustable or not, and we implement on different type of similar systems. So for implementing practically, of course, we need the IC, and we can use some interference to computer to implement it. But just it's for laboratory. In industry, so it's going to much more. Developing electronic to implement. But practically, if someone really design a fuzzy adaptive and implement it, is a huge work, and it's kind of innovation.
Mm-hmm.
So it doesn't mean it's impossible. For example, China is doing nowadays this, some European doing, but we need also some electronic ICs to implement it.
Mm-hmm.
But my opinion is first we need to implement in MATLAB, and first to see Python how much is trustable and can be extended for microarrays for different situations. Then after that we can implement by ICs, or at least interface some devices to computer to laboratory. It works that we can. But if we want to solve all the problems at the same designing, so it's difficult. Yes, dear professor.
Congratulations.
Thank you very much. Thanks for coming.
I remember maybe 25 years ago,
Yes.
I was researching this kind of subject, looking for chaotic behavior in power systems dynamics, but not power electronics, power systems.
Exactly.
There are a lot of researchers everywhere trying to identify some bifurcations and chaotic behavior and so on.
That's true.
But at that time, the experts in power systems, they didn't take this very seriously. It was difficult to demonstrate using real data that some chaotic behavior could happen, but we're able to find some kinds of bifurcations and purpose failures. It was very beautiful mathematical approach, but they didn't take this very seriously.
That's true, dear professor.
How about today? Everything is different because we're talking about power electronics, microgrids, and a lot of more complex dynamic behaviors. Because in power systems we have low frequency electromechanical oscillations, much more predictable dynamics, let's say. Power electronics, it's more complex.
Exactly.
But is it possible to demonstrate chaotic behavior using measurements, for example, experimental data in microgrids?
Yes, so this is the topic that nowadays they're working on. That is that time they left because of 2 reasons. One reason was computers, also machine learning research about some researcher that 20 or 15 years old machine learning. The research about computer cannot analyze the amount of data. And for example, countries like Japan, China, the Asian countries, they research a lot in that, and they didn't implement. And one of the things that before they search, find a good result is behavior. Because of one reason is computer. Secondly, was here a classic method that they try to implement. For example, by PID, they try to control by PID, or they try to recognize by old identification rate. But nowadays, intelligent control can help us to do it easily, especially. And as you can see, for example, myself, I designed three different controllers for chaotic systems or difficult chaotic systems. That if I want, for example, myself as a control engineer, if I want to design by backstepping, for instance, difficult stuff, I left this research because they take my time. So this is the issue there. Of course, we can if we find the problems, because as I mentioned in the previous seminar, the first thing for a control engineer is what I'm going to do. I'm going to, for example, control what? I'm going to solve which problems. So based on this, of course, we can discover the chaotic behavioral system and try to see what kind of problem happens after chaotic behavior. Because when system acts chaotically, many problems will evolve, like different harmonic, different frequency, different switching. And nowadays, it's open question for researchers that they are looking for. Thank you. Any question?
I think you leave back in the campus microgrid, in which we all the loads are connected using the medium voltage connection. So we have 10 transformers. So the black starts a problem. But at the beginning, we have only the transformers.
True.
And the start task is very complicated because they use strain, the rush current, how the solution for a while is we turn off everything and start slowly to avoid to maintain the transformers in the linear region, to avoid the saturation and see. But this we have we have to turn off all the loads, and it's not possible to have a senseless transition. If you try, maybe we would find a lot of problems with many converters trying to work together and use a non-linear device
Exactly.
like the transformers.
Exactly, Professor. Because in for example, Texas University or Michigan, nowadays they have 3 open topics for control. One of them is power system, power electronic, and microgrids. So also Europeans get focused on this. And another is robotic, another is economic. Because nowadays they are extremely, as you mentioned, they are standing. And dynamic become more and more complicated based on new devices. And new devices also have more complicated dynamic. That's where it's much more important. Okay. And another thing that I want to mention here in the speech is still researcher control divided into parts. One part do believe in classical way, and some part believe in intelligent way. I mentioned in the previous seminar also, and now it's going to repeat again. For example, myself, I provide a paper about fuzzy or chaotic system. I send it to the journal. It has really no value because I solved some problems. When I receive an email from a editor, it was directly rejected. The reason our editor said this work is not fit for our scope, because they don't believe in intelligent way, because they believe it doesn't have the maybe huge mathematical background like a classical person. As you can see in fuzzy, we don't need the exact dynamic of the system. So we are engineers. We are going to solve the complicated problems. We are not going to make it more complicated.
In power systems dynamics, so most of the people, they prefer the classic control theory.
Exactly. That is true. That's true. Good question.
Go ahead, John.
Okay. Hosein, I want
Just a moment, John. The audio is off.
I have another bit.
Oh, sure.
A microfonia. Alô, alô.
Go ahead, John.
Okay, can you hear me, Hosein?
Yes.
Yes, I going along the lines of the previous question, but from understand from a point of view of a control guy. So you have a kind of powerful tool for control, and that is very practical, and you can use it. Excuse me, in many ways, in many problems, as I understand. But you still, I'm very curious about the idea behind, because you still need to, when you say adaptive control, you still have to rely on some kind of identification, of, at least of some important parameters, to have I guess you don't really know the dynamics of your system, as you said, but you need to a step of identification that may be prior to the control or during the control. But so you have associate a kind of learning period or learning phase where you still are trying very say conservative with your control, and then when you got something that you recognize it, and as you are getting more and more data, then you feel, say, more comfortable, your control feel more comfortable to apply a stronger control. And so this is one idea. The other is you mentioned also that you need to work with Lyapunov to get stability, and that's probably the most general idea of getting stability so far. But you still need some special data or special structure of your system to construct a Lyapunov function, or in the fuzzy control you don't need to rely on some specific structure. You can build it from this knowledge that I just talked before. How do you see this? Because I'm very curious how these new techniques and new views that you mentioned stick together with the old and more new things.
Sure, thank you, Professor. Thank you very much for your question, first of all. Powerful question. As I mentioned, for this is the problem of fuzzy, I mean pure fuzzy. If you want to hire the pure fuzzy, so we, for example, for many parts we have problems. That's why we switch to adaptive fuzzy. For example, for proving stability, for training membership functions, we cannot use by manual. So definitely we need some algorithm to adjust the membership function and rules in fuzzy. Because as you know, fuzzy also has its own mathematics, but the way that fuzzy talk, the way of mathematics talking, is different with classical. For extracting the model, so of course we need some information from the system. For example, in robotic, we measure the force. I'm talking about dynamic. We don't know dynamic of the system, but definitely we have some information about behavior of the system in the control perspective. Because for control engineer, dynamic is important, not the name of the system. For example, we just look at the mathematical dynamic and we design the controller. So we get some information based on the performance of the system, like lifting something, like force, like other things. In power electronics, like voltage, for example, coming to the converter, like the output of the converter, but we don't know the dynamic. So this is the question. But for proving the stability, of course, after when we are going to prove the stability, we use the pure mathematics.
I mean, we extract the model, we gave it to the controller, then design. Now we are going to prove the mathematics. So it's same as classical way. So we need to prove mathematically. We upon a function, find the Lyapunov function to reach to that condition, or other lemmas or other theorem to prove the stability. Sometimes this finding this Lyapunov function is difficult. We need to design compensator to reach to that function. So for pure fuzzy also, so two types, so two parts for replying your question. For proving stability is same as classic control. But for designing fuzzy, also we cannot use the pure fuzzy. We need to have some algorithm to train the fuzzy. Then after we extract the model, just we use fuzzy for estimation here. Yeah, at least in my work, of course, has a different type of application, classification, observation, estimation, control, direct adaptive control. But when we extract the model, so we give it to the control, classic control. But the novelty is we are not dependent on the model of the system, because in the classic way, you took the model of the system, you designed the control. So if model change, all your designing change. But in fuzzy, since it's especially fuzzy type 3, that it's online change adaptive. I mean, we adapt the parameter online, time by time. So it's not dependent on the mathematical model. After we have the adaptive model of the system by hiring fuzzy, we give it to the controller, so this controller can be able. And after this, so everything is same as before, for proving stability and other things same as before. We need to find that difficult function that, of course, sometimes very difficult. I hope I convey my message.
Okay, thank you. Thank you for a nice seminar too.
Mais alguma questão?
Vou tentar falar muito pouco. It's more simple, my question. Why do you use the function, fractional order function to choose a model of reference model? The D, can integral with D. This model is a model of reference model of adaptive function. Yes.
No, the fractional order is another way to describe dynamic. You can use the, let's see. You can use the normal one, as you can see in your works, for example, in your thesis. Just go through that. Or you can use the fractional order. Fractional order gives you the better description of the dynamic. It's not about control, it's the system. I use the fractional order to describe.
It's a model of reference.
System, yes, not a system. My system was creative system. Yeah, I describe it by mathematics. As in transformer, how you describe transformer by circuit, and you discover some mathematical, right, by KVL and inside. So here we describe the dynamic of the case system by this fractional. But why fractional order? Because it gives you the better description. Because even in every system where you have the dynamic, okay, definitely it's not exact. It's similar. For example, the transformer is a good example. In transformer, sometimes you consider the parallel branch. That it's big because you see I3 is less, is a few, so we can remove it. But it's not true. Actually, you cannot remove it because you have IC, but we want to make it simple, right? So every dynamic model has some problems, and they are not have some problems. They don't describe very well. I use the fractional order to describe it very well, to describe everything, every nonlinearity part.
And the fractional model can describe more than it's better.
In this case, was better, yeah. But it's a new knowledge in mathematics, not new, but it's a mathematics for 1,000 years ago, the fractional order is for 300 years ago. It's novel in mathematics, fractional order. It's kind of a different way to design. It has its own advantage. You can search on Google Scholar of that. For example, in robotics, some nonlinear terms, they not appear when you use the normal way. Bifractional or the diagonal.
And how find this type of model to describe something?
So
It's more simple.
yes. So, I told you before we have a kind of knowledge and control. We call it identification. Identification, yes. We can or not just identification and control. For example, some mechanical equations that involve in your system. For example, synchronous machine. Right? So you can see sharp described by this equation. I don't know, for example, any other thing described by specific equation, right? But for some systems that they are really difficult to discover this, we have an identification way. We give some data to this block, we get some data from the block. Based on this data, we can find by some, for example, regression, linear regression, and linear regression, we can find the data. Even the component is not exact, because we ignore a lot of things. But the positive point of positive here is we are not dependent on that data. Of course, we need to have the structure, but it's not dependent. Every parameter change, because it's not the basic work of the fuzz. But if you want to learn how fuzz works, you can.
Sem som aqui, Antenor.
Algo mais, gente? Então, não temos outras questões nesse momento, mas vamos ficar pensando em boas questões, depois a gente pode enviar para o Hosein new questions and maybe new challenges for this kind of systems. And so, Hosein, thanks again for the presentation, and I hope to.
You're welcome. Okay. I can pass my email here if someone.
Thank you, Hosein. Valeu, Antenor. Obrigado.
Thank you. See you.
Okay, então, aí no chat tem o e-mail, Hosein, então, se alguém tiver as questões, está disponível. Okay. Okay.